There's bell work. It's a good bell work. Nice, good 5 questions right there. And there's our answers. And yeah, remember this little caret button. It's just one button to the left and one button up from the button 7 right there. All right, here's our objective for this lesson. I can use properties of products and quotients of powers to simplify expressions. Just take 1 minute to copy that down, please. So we have seen that before, multiplying the same bases, then adding the exponents that go with those bases. But this other one, quotients of powers. Quotient is division, and generally we see this with division, like this one. So if you take a base, the same base, and divide it, then the 2 exponents that you have, use the same ones, well, you're going to keep the same base, whatever it is. And yeah, this could even be with fractions or decimals or letters or numbers, doesn't matter. But the 2 exponents, A and B, since we're looking at division here, you would end up subtracting those. Now, the order of these will matter because we know that order does matter for subtraction. It's always the exponent of the numerator, and then you subtract the exponent from the denominator, okay? And we'll look at why this works this way here in just a moment. Yeah, complete columns 2 and 3 in the table below. We may do them a little bit differently though. All right, so just to start out here, we'll do 5 to the power 3 times 5 to the power 2, okay? So 5 to the power 3 I'll do in red, 5 to the power 2 I'll do in purple, and yes, again, we have seen this before. Well, 5 to the power 3 would be 5 times 5 times 5, and then of course it's still being multiplied right there, so we're going to show multiplication between both of these expressions. But then in purple we got 5 to the power of 2, so that's just 5 times 5. Now the thing about this is that the bases are all the same. So that means that since they're all the same, I can keep the base the same. But since additionally they're all being multiplied 1, 2, 3, 4, 5 of them, then that 5 there is the new exponent 2. So it simplifies this expression, and just like we've talked about before in the last lesson, when you're multiplying the same bases like we just saw right there, the 5s, you can take the 2 exponents, which was 3 and 2, and just add them together. Okay, so when the bases are being multiplied, just add the exponents together. That's it. All right, and it's going to work. Let's do that third one with the y's here. So again, I'll split it up. I'll try to color code it so it's nice and pretty. But I got y to the power of 2, so that would be y times y right there. And then y to the power of 10, just maybe a little rough, but I think we can do it. Y to the power of 10, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 y's. And again, these are all being multiplied, which is important to know. Because then we have y to the power of 4. I'll do that one in green. So that's 4 y's being multiplied. 1, 2, 3, 4. All being multiplied right here. So again, we see that it's the same base being multiplied over and over and over. So we're going to keep the base the same as y. But then we just got to count how many there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 of them. There we go. So that would end up being y to the power of 16. Now, of course, just going back to what we did before, since it's all the same base, yes, of course, it's possible to take that same base, which was y, and then the 3 exponents that we had, which was 2, 10, and 4, and you could have just added those exponents. Okay, and again, we've seen this property with exponents before. So yeah, as of right now, we're just looking for these things in exponential form. So yeah, could you evaluate 5 times 5 times 5 times 5 times 5? Yeah, you could. And you could use a calculator to do that, but that's not the actual answer we want in these types of problems here. So b to the power of 6 times b to the power of 2. So I'm going to start with b to the power of 6, and I'm going to expand these first, and then we'll show the rule, and we'll see why the rule works. Okay, so b to the power of 6, that's 6 b's, 1, 2, 3, 4, 5, 6. And then I got b to the power of 2 there, so that's b times b right there. And yeah, we can show multiplication between all these. In fact, it's even showing the multiplication right there. So there it is. And now, And since we're looking to change this back into exponential form, what I would do is I would count how many b's there are, because it's all the same b being multiplied. So I can use exponential form because we're just having repeated multiplication of the same value, b. And I just need to count those. 1, 2, 3, 4, 5, 6, 7, 8. So that would end up being b to the power of 8. And so having known the rule now, we're going to take that base b and the two exponents, which were 6 and 2, since they are being multiplied there, we would add those two. The bases are being multiplied. We're adding those two exponents. And 6 plus 2 is 8. So that's how we get that new exponent. All right? And then this next example, this one we got some different values, and that's good. It's good to see that stuff. Like right here, I'd look at 3 and 2. They're not the same base, but they're similar bases. So I'm actually going to use some commutative property multiplication to just move these closer to each other. 3 times 2 right there. And then if I expanded my x's, I got 2 x's right there and then 2 x's right there. They're all being multiplied. X times x times x times x. And then over here with my y's, I have this 1 y and then 2 more y's all being multiplied. So bringing this back down into its more simplified format with exponents. There we go. Well, I see 3 times 2, which is 6. Then I've got my base x, and I've got 1, 2, 3, 4. 4 of those x's, so that's x to the power 4, because they're all being multiplied. Then I've got a base y, and I count 1, 2, 3 of those. So that's y to the power of 3. Okay? Now this is really how we're going to break these problems up if there's lots of different bases, even if we start using division, which we will. I would start focusing on just the numerical bases and then go through each letter base individually. Okay? Well, what about the rule? Well, yeah, let's apply the rule on this one. Not really with 3 times 2, but with the base x's. We saw here that there were 2, and then here there were 2 as well, so we just added those. And yeah, that's how we got that x to the power 4 right there. Now the y, sometimes this one ends up being more tricky than we wish it was, but you got a base y. We know there's the 2 from these, but some students would say, well, how many y's are right there? 0 or 1? It's 1. Okay, that's one of those phantom ones we've talked about from the last lesson. So that's why it's 1 plus 2, which, yeah, that's that 3 right here that we got. So you're welcome to put multiplication between these. Between letters, we don't really need it, but you are welcome to use it. Same with like letters and numbers, like the 6 and the base x right there. Now, if I was multiplying between two numbers, I would make a point to show the multiplication just so we don't get it confused with multi-digit numbers and place values. Because yeah, so as soon as you see that the same bases are being multiplied like this, you can just take the two exponents, whatever they are, and just add them together. So of course, a and b would be numbers, and it is possible to have a variable base, just like we saw with the base y's in that last slide. Yeah, just take those exponents and add them. All right, so how would you simplify a times a to the power of 3? Well, of course, and we've talked about this last time as well, that a has an exponent, it's a phantom 1 right there. So since it's the same base, you can keep the two bases, or the same base, but the two exponents, 1, and then this 3 right here, you're just going to add those together because the bases are being multiplied. So this would end up being simplified as a to the power of 4. And that would be considered simplified. Okay, so you can just add the exponents. So let's simplify this one. Okay, and again, all the bases are being multiplied, and with multiplication, of course, we don't usually show all this multiplication right here, but it's there. And that's important because when the same bases are being multiplied, you just add the exponents. So where we have this base 8 right here, it's not showing an exponent either, so I'm just going to keep that 8 the same. Okay, and that 8 is a base, not an exponent. It's very different. Then my first variable, I'll look at the variable a, or unknown, and then we'll look at b. Okay. Before my a's, I have exponents of 1 and then 2. And again, this was a phantom one, this first one right here. So I'm going to take those two exponents, 1 and 2, and add them together because the bases are being multiplied. right? That would end up simplifying as a to the power of 1 plus 2, which is 3. Okay, then the base b has exponents of 5 and then another phantom 1. So 5 and 1, we're going to add those two exponents because the bases are being multiplied. So that would end up being b to the power of 5 plus 1, which is 6. b, the base, to the power of 6, the exponent. And yeah, don't forget the 8 there when you write this down finally, because that's part of the expression in the end as well. So g is kind of like the last one in that table, right? We got, and yes, this is multiplication between these. This is just a different way to show multiplication between parentheses. And remember, if you ever do not see the operation, it has to be multiplication. So right here, I'm just kind of separating these by the type of base that we're looking at. And so I see the 2 and 4. So I'd say, yep, 2 times 4, boom, that's 8, right? So I wouldn't really necessarily look for this as an exponent, although you could. But that's a little bit beyond what we want to go through right now. And then I'd be looking at my base x's. And again, this is all multiplication throughout. And once again, I got that. That's x to the power of 1 right there. So there's one of the exponents for x. And then we got this x to the power of 2 right here. So that's another exponent of 2. Since we are looking at multiplication, we'll be adding those two exponents. So my base x will end up having an exponent of 1 plus 2, which is 3. And then base y's as well. We got a base y right here. That exponent is 1. So I'm going to show that exponent down here when I show my work. And then I got a base y here. Again, this is all multiplication, but its exponent is 3. But since it is all multiplication, I'm adding those two exponents. So this ends up being base y to the power of 1 plus 3, which is 4. Now this z right here, there's not really anything to do with it. It's just out there. So I'm going to leave it there, okay? But if I wanted to just write my full expression simplified in exponential form, I keep the 8. I've got my x to the power of 3. I've got my y to the power of 4. I can do better 4 than that. There we go. And then we have the base z as well. And yeah, this is actually the final answer we'd be looking for on this one. All right. For this one, we'll start with this second one actually right here, the a to the power of 4 over a to the power of 3. Start with that one. And so I got a fraction line, right? Just like it shows in the problem right here. So I'm going to keep my fraction line, and then I'm going to just expand the numerators and denominators. By the way, after we learn the rule for this, I will no longer be expanding these. Not just because it's a waste of time, but it's more convenient just to learn the rules, which is kind of what we're trying to get to. And that's the objective for the day as well. So right off the bat, I got a to the power of 4 in the numerator. That's a times a times a times a in the numerator. And then in the denominator, it's a to the power of 3, so that's 1, 2, 3 a's, all being multiplied, by the way. And we've seen this before, where something divided by itself is, just 1. 1 and 1. So remember, I think I've said this before, but in the past, particularly in elementary school, sometimes they'll say stuff like, hey, this cancels out. Well, you could say that depending on your interpretation, but it's not necessarily that they're canceling out, they're just becoming phantom ones. So that means that if I wanted to rewrite this expression, I just wouldn't show the phantom ones, right? I'd say, well, it's just a right there. And well, you could put this over 1 if you'd like. It's not really necessary that you do. In fact, make it fully simplified, just write a right there, okay? Now, just so we understand, and this is important as well, that's really a to the power of 1. So the final expression here, yes, is just a to the power of 1. But the bigger question is, what is the shortcut? And you see, back here when we was crossing these out as phantom ones, it's kind of like we've taken them and subtracted them from the exponents, right? So that means what you're going to do, if you take the same base that's being divided, in this case with this fraction line, then you take the exponent of the numerator, and then you're going to subtract the exponent of the denominator. So that's why you'd get 4 minus 3 there, which is 1. And that would give you a to the power of 1. Now, of course, I'm going to make that a phantom 1 right there. So it's just a. But that 1 is still there. That exponent of 1 is still there. It just made it a phantom 1, so you can't see it. Which is why phantom numbers are so creepy. Okay? So let's do this fourth example here first. Okay? So again, I'm going to set this up with my fraction line just to start out with. One looks like it's kind of a big one. And so I got 4 to the power of 5. So that's 1, 2, 3, 4, 5 fours all being multiplied right there. And then we got x to the power of 7. So 1, 2, 3, 4, 5, 6, 7. And then in the denominator, we got 4 to the power of 2. So that's 4 times 4. And then x to the power of 4. I am separating these on purpose, of course, just so that they line up a little bit better. But it is actually still multiplication between, and that's okay. Well, just like we've seen before, anything divided by itself is 1. So 4 divided by 4 is 1. 4 divided by 4 there is 1. Phantom 1, they're going to be phantom 1s. And then x divided by x is 1, no matter how many times you do it. So there's just a bunch of 1s right there, okay? So what do we get? Well, in the end, we end up with the base 4. And there's 1, 2, 3 of those 4s left that were not crossed out as phantom 1. So that's 4 to the power of 3. And then I also have a base x. And how many of those there? 1, 2, 3 of those. So that's also x to the power of 3. All right, so I got 4 to the power of 3 times x to the power of 3. And yes, if you prefer, you can put the multiplication between them. But I'm a lazy math person, so I'm not going to do that. Now I'm going to apply the rule on these, okay? So we had the base 4 and the base x. So again, you take the exponent from the numerator. So I'm looking at base 4 first. That was an exponent of 5. And then the denominator exponent was 2. And then, yeah, we just subtracted those two. So that would be 5 minus 2, which was 4 to the power of 3. Now, if it wanted us to evaluate, it would be 64, but that's not really important right now. We just want to learn about the rule here. Then for my base x's, I had x to the power of 7 in the numerator, and then x to the power of 4 in the denominator. Of course, those are subtracted because the bases are being divided. Okay, so just right there, we've seen when we're multiplying the same base, you add the exponents. When you divide the same base, now you subtract the exponents. That's 2 operations out of 4 basic operations in math. Of course, we'll look at multiplication of exponents as well, but division of exponents comes more in 9th grade stuff. Okay, and this is important to notice about the a's. On this one, when we did the division, there were more a's in the numerator, which is why we ended up with a to the power of 1 here in the numerator. The only reason I'm addressing this right here is because it is possible to have just an a in the denominator, in which case you'd have 1 over a instead. I mean, you may be feeling like this is pretty complicated. Some of you may be feeling like this is not so complicated. It just depends, but hopefully with some experience, especially from the assignment and tests and quizzes, you'll feel a little bit better about this stuff. So let's do this top one here, 3 to the power of 5 all over 3 to the power of 2. Now this is a fraction, so I'm going to keep it as a fraction. So there's my fraction line. And in the numerator, I got 3 to the power of 5, so that'd be 5 3's multiplied. 1, 2, 3, 4, 5 3's, all being multiplied. And then in the denominator, I've got 3 to the power of 2, so that's 2 3's being multiplied, like this. Now this goes way back, but we know anything divided by itself is 1. So this 3 divided by 3 there, 1. And this 3 divided by 3 here, 1. In fact, since those are 1s, I'm going to make those phantom 1s. So just be careful, because in the past they've said stuff like, oh, it cancels out. And it's, I mean, that's one way, I guess, to express it, but it's not really that they've canceled away, like they've just gone away or evaporated. They're just phantom 1s. They're there as 1s, you just can't see them, okay? But now what we have is base 3, because we have 3 repeatedly being multiplied by itself, and I count 3 of those. So that's 3 to the power of 3. Now applying that rule, which we saw in the objective, I'd say, well, look, you're going to take your base 3, it's true, And then you take the exponent from the numerator and the exponent from the denominator, which, by the way, should be second-handed. Yes, this order does matter. Since we're dividing the same base, we're going to be subtracting those two exponents. And yeah, 5 minus 2 is 3. All right, so this next example here, the third one, b to the power of 3 all over b to the power of 5. Now again, just because we've seen this before, since we are dividing the same base, we'll be subtracting the exponents. If we were multiplying the same bases, like we've seen before, we would be adding the exponents, two major operations that we've gone over for mathematics. So I'm going to expand this one again because it's so fun. All right, so I got b to the power of 3. I'll do this one, I guess I'll do it in green here. So that's 3b's being multiplied in my numerator. And then in my denominator, I've got b to the power of 5. So that's 1, 2, 3, 4, 5b's in my denominator. Okay? And yeah, we're dividing these. So anything divided by itself is 1. So there's a 1, there's a 1, and there's a 1. And yes, since those are 1s, and now they're being multiplied, I would change these then into phantom 1s. But what do we get out of this? Well, look, we get, in the denominator, I've got b's being repeatedly multiplied. There's 2 of them, so that's b to the power of 2. A lot of times, students get mixed up at this point because, I don't have anything to put in the numerator, and sometimes they'll put a 0 right there. That's not true. Remember, we made those phantom 1s. That's why it's confusing sometimes to think of those as canceled out. It's not that they're canceled, they just disappeared as phantom 1. So we're going to show that phantom 1 there in the numerator because we need something to put there. And a phantom 1 is, well, it's appropriate. Okay. Now, that's one way to write this expression. I'm going to write it over here. 1 over b to the power of 2. But something else occurs when we apply the rule for this one. We take the same base, b, because they're being divided. I take the exponent from the numerator, and then I would subtract the exponent from the denominator. Probably should have color-coded that, but I didn't, dang it. And what do we get from this subtraction? Well, now it's b to the power of 3 minus 5 is negative 2. Now, does this mean that they're the same thing? Yes, it does. B to the power of negative 2 is exactly the same as 1 over b to the power of 2. Now, I'm pointing this out that it is possible to have negative exponents. We know this because we can subtract the exponents. But we'll deal more with negative exponents and some specifics next time. Yeah, no, I don't mind. It's not too bad. It's just an extra rule. So the subtraction comes from this crossing these out as phantom 1s, right? Anything divided by itself is phantom 1. So that's why we end up subtracting these types of problems with dividing the same bases. It's good stuff. All right, so this is the rule. Yep, once again, if you're dividing the same bases like this, then you just take the exponents and subtract them. So that sounds good. Yeah, so on this one, notice the 6, the 6 base has no other values to operate with. So yeah, that's going to stay 6 right there. And then the base c, though, yeah, you're going to take that exponent from the numerator, 5, and then the exponent from the denominator there, 2. And yeah, since it's being divided, those bases are going to be subtracting the exponents. So yeah, it does end up being 6 times c, and then 5 minus 2 is 3. Now, just be careful, and I'm pointing this out because next year when you go into math class, I really don't care so much because I'm okay with the small, I think the small breakdown in communication here is acceptable, but just so you know, other math teachers will not accept that. If you said 6c to the 3, like next year, your teacher's going to freak out about that, okay? I'll be like, what the crap are you talking about? 6c to the 3. Again, I don't care so much, but other teachers are going to be like, it's 6. It'd be 6. I'm talking about the answer. 6. This would read 6 times c to the 3rd power. All right? It's a small technical issue, but there's some math teachers out there that the moment you say that is the moment they freak out. And I've talked about math people freaking out. It's not good for society. It's not good for your neighborhood, okay? It's not good for school either. Sometimes it's caused explosions. You just never know. That's a good question. If there was like a base 2 right here, you could just do 6 divided by 2, but be careful with that because some students, since we're using specifically subtraction with the exponents, I'll say, well, 6 minus 2 is 4. Well, it's division of the bases, so you got to actually divide those. So be careful not to get these rules of exponents mixed up when you're dealing with bases specifically. So on this one, we got 3 different bases. So let's address all 3. A, B, and C bases, okay? Now let's focus just on the A's, and it's okay to focus on one at a time. And I'm going to start with the A's, just almost alphabetically. But I see the 1 exponent for the base A in the denominator right there, which means you can take the exponent from the numerator, which is 7, and subtract the exponent from the denominator, which is 1. All right? So let's give ourselves a little bit more space here. That means that this would end up being a to the power of 7 minus 1, which is 6. And then our base b's, I've got an exponent of 10 in the numerator and then an exponent of 3 in the denominator. Since those bases are being divided, we're subtracting the exponents. So base b would have a new exponent of 10 minus 3, which is 7. Now, I put the c here just kind of in a list with these other bases, but there's only one c base in this problem, and it's in the denominator. So actually, I should probably rewrite that instead of with the base a and b. It should just stay in the denominator like this. So that's going to show a to the power of 6 times b to the power of 7 all over c to the power of 2. And so exponents of 2 and 3 are unique because when you get an exponent of 3, you can say it's cubed. And when you get exponents of 2, you could also say it's squared. So that could be also communicated as c squared right there. Okay, for problems like this one, yes, we are dividing, which is good. We like division, not as much as addition or counting, but it's okay. And yeah, we got two different bases on this one, so I'm going to focus on each base separately: x's bases and y's bases. Well, since we are using division here, I would take the exponent from the numerator, and again, I'm just starting with the base x's. So that's 20 in the numerator exponent. And then I got 15 in the denominator exponent. Since we are dividing these, we're going to be subtracting them. All right. So yeah, that's why we're subtracting here as well. Remember, these 15 here would cross out 15 of these 20, which is why they're just subtracting, crossing out as factor 1. Well, then we get base x to the power of 20 minus 15. I get 5 right there. Okay, so that's my first factor in this expression. I'd have x to the power of 5 right there. Let's look at our base y's, though. In the numerator, I got 15. So I have to start with that one. And since we are dividing the same bases, we'll be subtracting the exponents, the second exponent from the denominator, 14. So I evaluate just the exponent there, 15 minus 14 is 1, which I will show is just y. Okay, I don't want to show that exponent of 1, although it's possible that it may want you to in the homework. So I'm just going to write this as x to the power of 5 times y right here. So on this one with c, we're gonna focus on just the numbers. Yeah, let's fix that. 2 over 8, it's not 4, it's 1 over 4. There we go. That's good. And I'm just going to kind of extend that line just in case there's exponents in the numerator and denominator. We'll see. So that takes care of the numbers, and then I'll focus on my base m, and then I'll focus on base n. Well, base m has exponents of 2 and 5, 2 in the numerator, 5 in the denominator, and these are being divided, so we're subtracting. Now, do remember that the order of the exponents does matter when you're subtracting, because with subtraction, order matters. There's no commutative property of subtraction. So that would end up being, well, m to the power of what is negative 3. And while we haven't seen negative exponents yet, we will eventually in more detail. But for now, one thing that you'll want to look at is, see how there's more m's in the denominator than the numerator? There's 2 m's in the numerator, 5 m's in the denominator being multiplied. That means that this m and its exponent of negative 3, it just needs to be in the denominator. So that will be m to the power of, not negative 3, but just 3. Again, there's more on that later. More on that later, okay? Now we got exponents for base n, 5 in the numerator, 2 in the denominator, so that'd be exponent of 5 minus 2. That'd be n to the power of 3. So see how there's more n's in the numerator? So my base n here is going to stay in the numerator. N to the power of 3. And yeah, at this point, I'm just going to make that a phantom 1 from the 1/4 right there. So this is what we end up with in part C right here. On these two, we got a, so 6 times x to the power of 2 all over 2 times x to the power of 4. Two different bases, again. So I would start with the numbers. That's 6 divided by 2. And again, this is a common mistake that we see with students. We get so used to just subtracting the numbers here that eventually some students are just like, yeah, it's 4. But that's 6 divided by 2, not 6 minus 2. Remember, we subtract the exponents, not the bases on this. So don't do that. Don't do that, okay? Unless it was 4, but this is not 4. 6 divided by 2, I get 3 out of that. Well, that's 6 divided by 2, but what about the x's? So let's look at the x's. Now, I would take the exponent from the numerator, 2, and I take the exponent from the denominator, 4, and since we're using division here, I'm going to be subtracting those two exponents. Well, this ends up being x to the power of 2 minus 4 is negative 2. Now, in the assignment, I believe that it does not want this as 3 times x to the power of negative 2. I believe. It is possible that it will. But if it wants only positive exponents, then just think about it like this for now. We're going to go over more negative exponent stuff in a future lesson, but see how there's more x's in the denominator than in the numerator? There's 2 in the numerator, 4 in the denominator. That means that the x's should stay in the denominator. So this is exactly the same as showing it as a fraction where 3 is in the numerator. But my base x is now in the denominator. But if I do that, then I need to make that exponent positive. Again, we'll talk about that in more detail next time. But for now, that's as far as we need to go on that. So the reason why the 3 is in the numerator is because 6 divided by 2, like if you were just to simplify this 6 divided by 2 right there, if you were to simplify that fraction, you'd end up dividing each of those numerator and denominator by 2. You'd get 3 over 1, and that's why this 3 here is in the numerator, because it should be in the numerator based on the simplification of the fraction. In part B right here, again, I'll start with the numbers. And it shows 8 divided by 2 here. And we know 8 divided by 2 is 4. Again, do not subtract those. It is not subtraction. It's division of those bases. And yes, we are dividing all the bases. But when it's the same base that we're dividing, we get to subtract the exponents. So on this next one, I got my s's on this. Let's look at my s's for this. Base s. There we go. And in my numerator, I got 12. So that's the first one I'll list. And then in the denominator, it's 10. And since we are using division here, we're going to be subtracting those two exponents. So my base s, when I do 12 minus 10, I get 2 out of that. Now, here's something interesting that happens with the base t's. Is you got a 4 in the numerator. So that's the first one I'll start with, and then a 4 in the denominator. And again, since we're dividing the same bases, we're subtracting the exponents. Well, everyone knows that something subtracting from itself is 0. But I want you to think about this because it kind of gives us a little front loading for the next lesson. Anything divided by itself is 1. See that? T to the power 4 over t to the power 4. So it's possible that they may want this as 1. On the assignment, okay? Just be careful on that one. So I'll show it. I'll show that both answers on this one, but in case they give you a base t, it would just have an exponent of 0. That's all. Well, what about my base u's? Yeah, let's look at those. I got base u right here, and I guess I'll use green. There's a 3 in my exponent for the numerator, and there's a phantom 1 exponent for my denominator for base u. So that'd be 3 and 1. Since we're dividing the same bases, we're subtracting those exponents. And this would end up being u to the power of 3 minus 1, which is 2. All right? So again, if by chance they didn't show base t in the assignment, that means that the final answer should look more like this. 4 times s to the power of 2, and then would make that t to the power of 0 phantom 1, and then you'd have u to the power of 2 right there, okay? So depending on how it's shown in the assignment will depend on if you need to show t to the power of 0, or if you just make it a phantom 1. So be very careful. Exponents are not multiplying by bases. That is not t times 0. That is t to the power of 0. That's very, very different. And we love that objective. I can use properties of products and quotients of powers to simplify expressions.